In this experiment, we're going to measure the distance between barbs on a hummingbird feather through diffraction. So a little bit on feather anatomy. This line right here, this is the shaft of the feather. You can see it here. And the hairs that grows across, those are the barbs. By using a caliper, I can get like a rough estimate of that distance, and I think it's less than 0.27, but it's hard to tell. So the idea is that we're going to pass a laser beam through the feather and measure the diffraction pattern on a screen, and from that calculate the distance between the barbs. It's really hard to hold a feather in front of a laser. So what I did is I punched a hole out of an index card, folded it in half, and sandwiched the feather in there. And then I taped it to this laser I got from Amazon. The laser has dial adjustments, so I can fine tune up and down and left and right with these dials. And I just use tape and a pipe cleaner to hold it in place. And then I zip tied it to the attachment mount on my tripod. Okay. Here's the laser mounted on the tripod, and by using a plumb bob, you can line up the very edge of the laser with your marking on the ground. The laser is set at 12 meters, but I have markers at 1 meter increments, and I'll measure the diffraction pattern at each distance. Here is the diffraction pattern at 12 meters. It's really important that you level the laser and you measure the height of the laser and the height of your target so that you can eliminate having to calculate a hypotenuse. And then using my caliper, I can measure the separation distance between the center and the next bright spot over. This is the data for my experiment. I threw out the first meter data point because it was 0.34 millimeters, and that is above 3 standard deviation from average, so confident that's wrong. I also left out 10 and 11 meter data points because I measured distance 1 meter at a time based off of the previous distance. So if any of the previous distance had an error, then the one after that would have the sum of all the errors. So by the time I got to 10 meters, I was no longer confident of how accurate my measurement was. So using calculations, I got an average of distance between the barbs, and that's 0.26 millimeters. And then I use Google Sheets line estimate function to get a slope for my graph. I added false, and this false gets rid of the intercept, so it just does y is equal to mx, no b. Here is the graph for my data. The x-axis is 1 over distance to the screen times the wavelength, and my y-axis is 1 over the distance between each barbs.